Well, we're going to talk about something really weird tonight. We're going to introduce you to logarithms, and this is totally brand new, and it's a pretty wild concept. And the one kind of overarching theme is it's going to be very similar to translating between two languages. You know, I think most all students are required to take some kind of foreign language course, whether it be French or Spanish or Russian or whatever it might be. And just like you spend a lot of time converting words and sentences from English into Spanish or whatever, and vice versa, from converting from Spanish to English, that's what we're going to work with today, is converting from exponential to logarithmic form and vice versa. So without further ado, we're going to try to set the table here, and we're going to get a few definitions out of the way. And the first thing we want to talk about is that exponential functions. And I'll tell you what, these are so important in real life. Exponential functions model so many different things that happen in the real world. Anyway, these exponential functions are of such importance to mathematics that they're inverses. And again, what is an inverse? That they're inverses, which are functions that reverse. Always think of reverse when we talk about inverse, their action. Well, anyway, these their inverses are important themselves. So whatever the inverse of an exponential is, it's very important, we've decided. All right. Now the inverse of an exponential function, and I'm going to abbreviate just a touch right there to fit it in, is known as a logarithm. So exponentials are very important, their inverses are very important, and the inverse of an exponential is called a logarithm. Well, we've got a lot going on this slide here, obviously. We've imported a lot of stuff. Don't be afraid to pause and get all the important stuff written down here. What we've started off with in this example is an exponential function. We defined f of x as being 2 raised to the x power. And it's already been graphed here on this axis for us, and we can see how it's increasing at an increasing rate, which makes it very exponential. And they've even given us a table of values. You said, well, if x is any one of these values, here's the corresponding y value, and those are the points that you see plotted on the graph over here. So they've done a lot of work for us to kind of get us set up. And the first question they want to know, well, is this function one-to-one? First of all, it is a function because it passes the vertical line test, and it's one-to-one because it passes the what? Yeah, the horizontal line test. So I'm going to say yes, and simply because it passes the VLT and the HLT. All right. In other words, we're saying each x value corresponds to one and only one y value, and each y value corresponds to one and only one x value. There's no repetition in either the x or the y list. All right. Now they said, part B, based on your answer from part A, what must be true about the inverse of this function? Well, we're going to go back in time and we're going to reference a very subtle definition that we talked about back in October, and we said, well, if the original function is one-to-one, then his inverse is guaranteed to be a function. So they said, what must be true of the inverse? Well, it's guaranteed to also be a function. That's how we want to answer that, guaranteed to be a function. Now, one of my favorite things about inverses is, sometimes we try to make them harder than they need to be. And we just have to remind ourselves, all we're doing is switching the x and the y value. So if I look at the first point up here on this table, I'm going to say, well, my new input is 1/8, and my new output is -3. Or the new x value is 1/8, and the new y value is -3. What I'm going to do is I'm going to go through my entire table, and all I'm doing is I'm switching the x and the y values all the way through the table. And then what I'm going to do is I'm going to walk over to my graph paper there, and then I'm going to start to graph that. So great time to take advantage of those graphs that you bought earlier. Rip out a really nice one and really plot these as neatly as you possibly can. So you can see over here in red these very little dots. I've tried my best to plot them as accurately as I can. Now 1/8 is kind of tricky. You're just going to have to estimate. 1/8 is just a smidge bigger than 0. But let's make sure it's smaller than 1/4. I want to make sure that that first dot is closer to the y-axis than the next dot above it and the next one above that. So relative to each other, they're progressively getting further away from the y-axis. Now I'm going to do my best to combine them in a very smooth, gentle fashion. And okay, it came close. Now, very important, and my graph doesn't do it justice. It should never touch the y-axis right in this region. It should get infinitely close, but never actually touch it. The other thing I want to make sure that we've got in our notebook here is this note right here. And I want you to use the appropriate notation as well. Be very careful that we want to say that the graph of f of x and f inverse of x are symmetric across the line y equals x, and that's the diagonal line we see here right in the middle. In other words, if we folded our paper right on that line, the two graphs would lay perfectly on top of each other. Okay, now the last thing we're going to cover here is we said, well, if we were going to find the equation of the inverse algebraically, what would your first step be? And they want us to just write down the first step and then stop right there. Well, the first step, now remember, this equation right now says y equals 2 raised to the x. So I'm going to switch the variables and I'm going to say x equals 2 raised to the y. And that's all they wanted me to do, is just write down that first step and then stop right there. And then we're going to build on that in a few moments. Okay, we're going to talk about how to define a logarithmic function and where they came from and everything. But again, your handwriting has to be extremely careful, and I'm going to do my best here. And hopefully you can do even better in your notebook here. But we're going to say that the function y equals log base b of x. Now notice the b has to be a very small subscript, just the opposite of an exponent. An exponent is called like a superscript. This is a subscript. And anyway, this equation is the name we give to the inverse of y equals b raised to the x power, which is a very traditional exponential equation. So for example, if I said y equals log base 2 of x, make sure the 2 is small and it's a subscript, that would be the inverse of y equals 2 raised to the x. So believe it or not, if you can remember what we just put in your notebook there a couple minutes ago on the last slide, y equals 2 to the x was the one that they graphed, and then this is the equation, log base 2 of x is the equation of the one that we graphed. I think mine was in red color. And then we're going to, okay, so we could build on that now, and we can say, well now, based on what we just did in exercise 1, do you remember how we switched the variables and we said the inverse is x equals 2 to the y? And now we know that these two are equivalent right here. So we can say, we can write an equivalent exponential equation. An equivalent exponential equation for each logarithm as follows. We could say that y equals log base b of x is equivalent to x equals b raised to the y. Now, it can get very confusing, and here's where we're going to practice converting from logarithmic into exponential and vice versa. But here's the key. I want you to understand that these two equations right here, these guys are equivalent. I'm sorry, those are inverses of each other. But then it's these two right here that are equivalent. And that's what we're going to talk a lot about today, is equivalency versus inverse. All right, just to warm up our lingo right here, I would say that the x value right there is the input. And then I'm going to say that the y value is the output. And that's some of the terminology we're going to use, just so we're all on the same page. And what you can see here, and again, we're saying that y equals log base b of x is the same as b raised to the y equals x. They're equivalent. That's what equivalent means. We're saying that these two things are identical. They're the same. They just might look a little different, but they're equivalent. Now what we're seeing here is the logarithm gives as its output, and of course output means y value, the exponent we must raise b to in order to produce its input, which of course is the x value. So that kind of sentence right there we might have to read it a few times, kind of take a step back and compare the sentence that we just wrote right here to the statement we have up here. But again, the output is the answer. That's the exponent we must raise the b to in order to get x. Notice how the y, what is the output over here, became the exponent over here. Now I think up to this point we've done a lot of crazy, goofy things tonight that are kind of a little overwhelming, and I think if you're having any trouble up to this point, I think we can clear it up right here on this slide. We're going to show you what I call an around-the-world trick that's going to help you convert from logarithmic to exponential. So let's say we're working with an equation that says y equals log base b of x. and we want to convert it from logarithmic to exponential. Well, here's what I call my around the world technique. Start with the subscript, which is the base. We're going to say b raised to the y, and you can even write the word raised right in there. Okay, raised to the power of y equals x. And again, you can write the word equals right in there on that rainbow, so to speak. Alright, so here's what it would look like. We would say b raised to the y equals x. And that's how you go around the world and you convert an equation from a logarithmic to an exponential. Now I want you to make sure you put in your notebook that these two equations right here, they're equivalent to one another. Alright, they are equivalent. It's just one's in logarithmic language, whereas the other one's in exponential language. And that's what we need to practice converting back and forth from. Alright, we've got a whole bunch of logs to practice evaluating, and that's what the directions are going to say. You can see it briefly here. I blew it up really large so some of the directions spilled off the side, but they want us to evaluate the following logarithms, and they encouraged us to do as many of them as possible without using our calculator. So what I'm thinking here, when I look at A, I'm thinking, well, it's got to equal something. So I'm just going to say, let's just say it equals x for right now, and now let's convert it to exponential. Let's go around the world, shall we? Let's say 2 raised to the power of x, in this case, equals 8. 2 raised to the power of x equals 8. So then you can just kind of solve it mentally and say, oh, I know, x has to be a 3. In other words, log base 2 of 8 equals 3. Alright, the next one here, part B. Again, let's say that it's got to equal something, so let's say base 4 raised to the power of x equals 16. 4 raised to the power of x equals 16. Piece of cake, x must be a 2. Alright, scroll across the side here. Alright, again, we need to set it equal to something, so that'll be the first step. 5 raised to the power of x equals 625. And here's where we may give in a little bit and play with the calculator, try a couple different examples. 5 raised to the third, 5 raised to the fourth, 5 raised to the fifth, whatever it might be. I think you'll end up getting x equals 4. 5 raised to the fourth equals 625. Let's say 10, let's set it equal to x here. 10 raised to the power of x equals 100,000. 10 raised to the power of x equals 100,000. Now, in this case, when you're raising 10 to a power, you just want to count the number of zeros. And in this case, we would raise it to a power of 5. So I think we're getting the hang of this. I think we're doing a little bit better with converting. These are going to get a little feistier because they're working with fractions now. So we're just going to assume that it equals something. 6 raised to the power of x equals 1/36. In this case, the exponent is going to have to be a -2. The negative thus giving you the fractional answer right there. Alright, let's say, not 0 equals x. 2 raised to the power of x equals 1/16. Again, because the 1/16 is fractional, we know that our exponent is going to be something negative. And I'm going to go with -4. 2 raised to the -4 equals 1/16. A couple more examples here that look like a lot of fun. Let's see. Log base 5 of radical 5 equals x. So let's go around the world. Let's say 5 raised to the x power equals radical 5. Now what I'm going to do is I'm going to rewrite radical 5 in the form of a fractional exponent. Anytime you have a radical, it's equivalent to a 1/2 power. Therefore, x equals 1/2. And then last but not least, probably the ugliest looking one, let's go around the world. We'll say 3 raised to the x power equals the 5th root of 9. Alright, again, let's rewrite the 5th root of 9. So I'm going to just say 9 raised to the 1/5 power. And now I'm going to get real sneaky because we just did finish a lesson not too long ago on using common bases. I'm going to rewrite the 9 as 3 squared. And then I'm going to multiply those two exponents. And so I'm going to say x equals 2/5, or 2 times 1/5, which gives us 2/5. So again, you'll see the theme is to just set the log equal to something like x and then go around the world, convert it to exponential, and it's a lot easier to solve. Alright, so we got just a couple of tricky questions left to challenge you with here today. They said, hey, if we're working with this function right here, y equals log base 2 of the quantity x plus 8 plus 9, And that's a tough one to read because you've got to, you've got to get the base 2 in there, you've got the quantity, and then you've got that plus 9 dangling at the end. If we were to graph it on the coordinate plane, which of the following, and this used to be a multiple choice question before I deleted the options, would represent its y-intercept? So here's the fundamental idea that you need to put in your notebook. When we're looking for a y-intercept, okay, and perhaps you remember this from a month ago, we are going to substitute a 0 in for x. Alright, so let's make sure this stands out in our notebook for tomorrow. If you're looking for the y-intercept, we're going to substitute a 0 in for x. So let's see what this looks like. We got log base 2 of the quantity 0 plus 8, which I can clean up here momentarily. So it's y equals log base 2 of 8 plus 9. And what we want to do is we want to practice, we want to just kind of evaluate this in our, we're going to have to do this one in our heads. For instance, I need to do log base 2 of 8 in my head. I'm thinking to myself, 2 raised to some power equals 8, right? That's what I'm thinking that's going on behind the scenes, so to speak. So I'm going to say that the log base 2 of 8 is equal to a 3. And then, of course, this 9's got to come down. So I got y equals 3 plus 9, y equals 12. The y-intercept would be a 12. And that's all because I substituted a 0 for x, and then I just solved it from there. The following question seems to be a very favorite style, or favorite question in the Regents exam stylistically. And they just want to know between which two consecutive integers. Now remember, integers are just, whole numbers, either positive or negative. Just picture the number line in your mind, 1, 2, 3, 4, 5. Between which two consecutive integers does log base 3 of 40 lie? So I'm going to take log base 3 of 40, and I'm going to do the best I can to evaluate this in my head. I'm going to set it equal to something, and from there I'm going to go around the world. I'm going to say 3 raised to the x power equals 40. Now, 40 is not a perfect answer with regards to a base of 3, but I'm going to do a little work off to the side, and I'm going to remind myself, I do know that 3 to the third power is 27, and I do know that 3 to the fourth power is 81. And because the 40 fits right in between the 27 and the 81, I know my variable has got to fall somewhere between the 3 and the 4. Whoops, that should be a 4. So because 3 to the third was too small, 3 to the fourth was too big, so 3 to the x is going to fall somewhere between the 3 and the 4, and that would be my answer. Between which two consecutive integers? It'd be somewhere between 3 and 4. Alright, we are finally allowed to use our calculator, and we're going to tell you what the calculator is capable of doing and what he's not capable of doing. Now, most of the calculators only have 2 logarithms on the entire calculator themselves. One's called log base 10 of x, and it's so common that it's actually called the common log, and it's typically written without the base 10. So if you see one right here, and this is super, super important that we get this in our notebook right here, this has to go in our notebook, that if you don't see a subscript, we are supposed to automatically assume that it's a base 10. And that's very, very, very common. And there is a button for this on our calculator. So if you're looking down the left-hand column of your calculator, about halfway down, right next to the 7, just to the left of the 7 key, is a button that says log. That is equivalent to what we have right here with log base 10. So when we evaluate this first one, we can type it into our calculator. Just go ahead, type in log 100, hit enter, and hopefully it spits out a 2 for you. We'll try it again. Let's try log, and then try typing in 1 divided by 1,000 and see what you get. Hopefully your calculator said -3. And for the very last one, you could go ahead and try typing in log of radical 10, and hopefully it says 1/2 is the answer. So those are some ones that you can do on your calculator. As the chapter progresses, we'll show you some more tricks to use on your calculator. But as of tonight, I just wanted to do a quick intro. We want to know that, so what are the most important things we need to know before we come in tomorrow? We need to know that the inverse of an exponential is a log. And we need to know how to go around the world. We need to know how to convert from logarithmic to exponential and vice versa. And last but not least, we need to be able to evaluate our logs. So if I ask you what the log base 2 of 8 is, hopefully you can do that pretty quick. If I want to know log base 4 of 16 or anything like that, those are ones that hopefully we can do in our heads without our calculator. So good luck, and we'll see you tomorrow.